Okay, here we go. Okay, it's getting a little bit tedious sometimes talking with these people. Some of these people, apparently they were taught everything in general relativity and all this stuff, but they still have like a mental block or something. So let's get into it here. Here we go. We have this one here named Kyle, and he got into discussion a while back, and he comes with all these very sophisticated points in general relativity. The local vacuum speed of light is constant for all inertial observers. There's no particular speed of light in a curved gravitational field. I don't know what it means by that. No particular speed of light. Well, there's a fixed speed of light in your frame of reference. So tell me how you can have the same speed with different measures of time and distance. And please send me your best scientist. So here he comes. He comes with this highfalutin language here. The parallel transport of vectors on a curved manifold is non-unique. So, for example, given a photon on an inward radial trajectory in the Schwarzschild geometry, the photon speed reconciled by an observer at infinity is twice the local vacuum speed v2c in the Gulf strand. Was it Painlevi coordinates, but v's velocity 0 in the Schwarzschild Drost coordinates. Okay, now he's talking about Schwarzschild radius, and it seems actually to agree with what I'm saying, what he's saying, but it's not exactly what I'm saying. So I said I never said the speed is more than 186,000 miles a second, because people don't get it. It still speeds up and slows down depending on the amount of gravity to contract distance and slow down time. No gravity means light is instantaneous. So he gets an idea of what I'm talking about. Says that's not correct. The coordinate speed of light can range from 0 to infinity in curved gravitational fields, which seems to agree with what I'm saying. You're also not understanding the condition of no gravity, which means that the Riemannian curvature is 0 on all components in gravitational field, is then globally the Minkowski vacuum. So you switch from one way of looking at it to another way of looking at it. Which means that the Riemannian curvature is 0 and all components in the gravitational field is then globally the Minkowski vacuum, for which all inertial observers measure the vacuum speed of light to be c. He's still not getting it. So I'm saying it's just a faster c when time is faster and distance is expanded. Have you done my 1001 thought experiment? So I explained the 1001 thought experiment to him. And he comes back a while later. See, this is 3 hours ago, and he takes a couple hours. And so 2 hours ago, he says, I think you need to get a book on relativity. You need to explain how you're synchronizing clocks in your hand example. So he did my thought experiment, and he saw what the problem was. He says, you need to explain how you're synchronizing clocks in your hand example as they clearly desynchronize. Well, that's kind of the point. And the faraway observer the observers of a black hole traveler to the observer observes a black hole traveler to redshift and dim in luminosity, which they always go to say, well, it redshifts, but it doesn't change speed. It redshifts or blue shifts, it doesn't change speed. They always go to that. They always revert to that. And he says, dims in luminosity. There's no observer speeding up or slowing down, which is just a choice of coordinates used by the observer. Okay. So he's kind of ignoring the fact that the person traveling toward the black hole looks stopped to us. It's traveling so slow, it looks like he stopped to us because of his measures of distance near the black hole are so much contracted, and his rate of time is so slow, it looks like he stopped to us. They overemphasize this point all the time, which is true, which is what's happening, but it's because the measures of time and distance are so much slowed down and contracted. So I say, okay, then I explain to him, the clocks are not synchronized since they're not running at the same speed. How are you going to synchronize two clocks running at different speeds? That is the problem. Are you going to try to synchronize two different measures of distance too? You can't. That's the point. It's the cause of the superluminal motion. The superluminal motion because of the distance from the center of mass. It's the reason everything in outer space is moving so fast by our measures of time and distance, which are not the measures away from the center of mass. They look fast, like they're going fast to us because they are going fast relative to our measures of time and distance. Because they have, in outer space, it's a changing rate of time. It is a changing measure of distance the farther away you get away from the galaxy. That's why you have superluminal motion. That's why you have clouds moving faster than the speed of light after an explosion. That's why you have plasma jets shooting out 7 times faster than the speed of light by our measurements, because you can't use our measurements. You can't use our measurements when you look at something in outer space, especially as the distance increases from the center of mass. You can't do that. You have to calibrate what the measure of time and distance is out there, because it's not going faster than the speed of light. It's going not even the speed of light. The motion is not even the speed of light. It's definitely not 7 times the speed of light. But it is going faster relative to our measures of time and distance. It is moving faster. At the same time as you have superluminal motion going faster, you have people that appear to be stopped, or things that appear to be stopped, moving near the black hole. This is happening at the same time. The point being is that you can have millions of years or billions of years in outer space pass by, while at the same time as 6,000 years are passing by on Earth. And it's even slower near a black hole. That's the point. This is simultaneous events. And anytime you change the measure, you're going to change the speed, which is what's happening, which is what they're not understanding. And it's just getting a little tedious right now to be explaining this over and over again. But sometime I was listening to somebody's talking about another subject. They said, you got to explain things 25 times for people to understand what you're saying. Probably even more. Anyways, that's what's happening at the same time. Now, this is simultaneously. This is at the same time. The speed, by our measures of distance, are exceeding the speed of light. So by our measures of distance in a 6,000-year-old Earth, The light from distant galaxies arrives instantaneous. It's exceeding our measures of the speed of light, but not the measures in outer space. I don't know why this is so hard to understand. Anyways, it's just another pet peeve of mine. And I mean, it explains everything. It explains everything. Here we go. Doki Doki. Hey, Jungle. Kelvin. We got Kelvin. We got Random Green TV. And Random Green. Okay. All right. Here we go. Let me see if I can read this. Okay. I wouldn't take it as seriously. You can't hear their tone of voice. Okay. I wouldn't take them seriously. You can't hear their tone of voice. JJ. Yeah, that's true. Okay. Kelvin, Kelvin, and Random Green, and Doki Doki. And that's about it. Anyway, so much for right now. Could you do a video of charts and graphs or something, or the speed of light and stuff? Well, what I do have is my thought experiment, which is a graph. It's mathematical. It's everything without needing the computer to do the math. And it's like a graph, and it's what I told this guy to do, which is right here. It says the changes in time and distance compound the changes in the speed of light as observed from our frame of reference. Do a thought experiment. Hold your hands a foot apart, representing 186,000 miles, saying 1001, representing 1 second, while pretending to see an imaginary photon going from one hand to the other. Now expand the distance, saying 1001 as fast as you can. You should note that the speed of the imaginary photon increases the more distance expands and the more time speeds up. Just the same as the farther away from the center of the galaxy it is. So it's the same as when you move away from the center of the galaxy, things are going faster. The opposite is also true. Someone moving in the direction of a black hole will seem to us to be stopped. If you change the size of a cubit, you will change the size of the house that you build with it. So let me just do a real quick demonstration here of the thought experiment. So, hello, am I moving? I'm not moving. Wait a minute. Anyways, let me see if I can get, oh, okay, here we go. All right, so this is the thought experiment. Hold your hands a foot apart, right? This represents 186,000 miles, and you're going to observe the speed of light, which is 186,000 miles a second. So you're going to watch the photon go from one hand to the other, which is 186,000 miles in 1 second. So you say 1001. That's 1 second that light travels 186,000 miles. That is c, the speed of light. Okay, when you get away from the center mass of the galaxy, distance is going to expand and time is going to get faster. So instead of saying 1001, it's still going to be 186,000 miles a second, right? The same 186,000 miles a second c, speed of light. But relative to us, it's going to be faster because you just changed the measures of time and distance. So instead of saying 1001, you're going to say 1001. And instead of a foot apart, it's going to be farther apart. So you're going to see the speed of light like this, 1001. You just increased the speed of light. You just made the speed of light go faster. And that's what happens without gravity in outer space. Distance expands, time speeds up, and that's the result. The speed of light is not constant throughout the universe relative to our frame of reference, relative to our 6,000 years of existence in this universe, in this earth, in this part of the universe. Elsewhere in the universe, time is going by faster. Light arrives from distant galaxies much faster, so that there's no time-light problem. Okay, that's it. I got stuff to do today, even though I'm not working. So God bless everybody. Take care. It's just a little bit tedious trying to explain something so simple that every scientist, anybody should be able to understand it. And I don't know why they have so much trouble with it. They get all in these complex explanations and everything. They don't even see what's actually happening. So anyways, God bless everybody. Take care and stay close to the truth and reality, and you stay close to God. You can't go wrong. And there's nothing to worry about if you believe in the Bible. There's nothing to worry about. Nothing at all to worry about. God bless. Take care.